Catherine, for the introduction. I'm really happy to be here today, so thank you for the invitation. Initially, I was planning to give more like a showcase of what we do at Lawrence Livermore National Laboratory, but then I decided it would be more useful for the students to go through some prediction metrics assessment and machine learning uncertainty bounds. And I tweak it a little bit, so I hope it's useful. And don't hesitate to stop me anytime you need for questions. So let's start. Okay, this is a little bit of my background. Catherine already talked a little bit about my bio, my expertise, but I wanna just say that I mainly focus on surrogate model verification, validation, uncertainty quantification, and data analysis. And I've been working in multiple physics problems, which I found very appealing. For example, during my PhD at University of Florida, I was in the Center for Compressive Multiphase Turbulence, which it was a center that was funded by the Department of Energy. And the problem was mainly related with fluid mechanics, where we were studying these multi-phase detonations where particle and fluid were dispersed, and we were interested in how particles rearrange after the detonations. Then at Los Alamos, the problems I was dealing with were slightly different. One was fracture mechanics, and actually I'm gonna show some part of that work here in this presentation. And we actually were investigating what happened when there are like high strain impact fractures in materials. And then the other topic was inertial confinement fusion. Basically, in that case, we were studying different parameters and input parameters on the design of the inertial confinement fusion design, so to optimize the yield. Like, we wanted to maximize the yield. This was very important, interesting project. And yeah, right now I work in atmospheric flow and transport hazard assessment problems at Lawrence Livermore National Laboratory in California. And as a data scientist, I was able to work in very different phenomena, as you can see, which is exciting. Okay. So I will start with an introduction, and why do we want to use machine learning approaches? Because it's like a hot topic and everyone is talking about these approaches, and what's the need and what's its appealing about these approaches. And these are some of my thoughts. For example, they can be used to predict outside the training window. Sometimes, most of the time they use for interpolation, but they can also be used as extrapolation predictors. Usually the predictions are fast if they are compared with physics models. And some applications may require many predictions. For example, uncertainty quantification and optimization are these kind of applications. And expensive simulations are hard to do if you need millions of them. So this is another use of machine learning. And then some of machine learning approaches can combine multiple fidelities to improve accuracy while maintaining low cost. And this is very desirable as well. Because if you can predict with high accuracy using low fidelity simulations, that's something that it's desirable. And then lately they're being investigated for transfer learning. Let's say that you have a lot of data on a particular problem, and then but you're trying to solve a slightly different problem, which you don't have much data. You can actually use your pre-trained model and transfer that learning to your new problem, which is, there is a lot of area of research in that. It's powerful. And then now some thoughts about why we care about uncertainty quantification in machine learning models. And for example, there is like this belief or this like lack of trust in these models, because usually, moreover, deep learning, they're usually treated as black boxes, right? So quantifying uncertainties can help to understand how they perform. And of course, if you give a confidence interval to your prediction, you will have more credibility. And when a problem it's very dangerous or expensive, you don't want to get it wrong. So it's good to have an assessment of the uncertainties in your model. And it's also I don't know, like give you a little more information about how robust is your model. So there are a lot of reasons why we wanted to perform this analysis. And this is the outline for my presentation today. So ideally, I will go through the first topic, which I will introduce some performance metric commonly used in geosciences. I'm tackling for 15 minutes there. Basically, I'm introducing a model that is K nearest neighbors, which is a very simple approach. And we're using that to predict the location of an air pollution plume driven by wind. The technique is enhanced using multiple techniques that I will go in more detail during the presentation. And the uncertainty in the predictions are assessed using metrics such as figure of merit in space, fractional bias, and this fact 2, which it's a measure of how far, like the fact that it has a 2, say like it's only considered as a good predictions they are like half or twice the value of the ground truths. And as I said before, these are commonly used in geosciences. And then my second part, the second part, I will talk about uncertainty bounds for multivariate machine learning predictions. And here we are using heteroscedastic uncertainty estimate to bound a multiple output neural network emulated. And the problem is high strain brittle fracture. And then hopefully we will have some time for questions. So let's begin. Okay, this is my first part of the talk. So problem of interest and the motivation for this work. So as I mentioned, I work in a national laboratory, and we are interested in this case to assess the potential consequences of a release of a contaminant into the atmosphere. Moreover, if this happens in an urban area. So how the plume will disperse will depend on different atmospheric conditions, but the good estimations can be done considering wind speed and wind direction. And this is what we will be doing in this to solve this problem. And the problem is reduced to predict the plume location after its release, given the source location and wind conditions. This is the description of the data. So in the figure, you have a map of a city. Here in black, you have the buildings. In white, you have empty spaces. And then here in green, the green cross means where the plume has been released, in which part of the city. Then this line, green line, shows the direction of the wind for that particular scenario. And then the plume is a plume of deposition after an hour of the release, right? And basically, in mathematical language, what we will have is we are interested in the output, which is the deposition, which is a function of x and y, right? And we have as inputs the location of the release, the wind speed, and the wind velocity, right? The wind speed and direction. And here I will give an overview of K-nearest neighbor, and I really like this machine learning or surrogate model approach because it's very easy, but also very robust. So the first step of this technique is to identify the nearest neighbor to the case that we want to predict. Let's say that we want to predict a case located, for example, in a certain location of the map with a certain wind velocity. We will have a distance. We will have like the training data, which is known cases, and we can compute the distance from the case I want to predict and the neighbors I have, right? And I would select the closest conditions, the closest release location and the closest wind condition to my problem that I do know or I do have data for. And the second step is sort that in increasing order, right? So we can choose the closest neighbors first. And then the third step is to make a prediction as a weighted average of the K-nearest neighbors. These can be weighted by the inverse of their distance. So the closest neighbors are weighted more, right? And the optimum value, well, and then you can have different values of the number of neighbors that you're using. And this will depend on the problem. For example, this is an example, a very simple example. So you can understand that what I tried to describe before. For example, let's say that we have this regression problem. We have some heights and some widths. And for some height and some width, we have some values. These values can be temperature, can be a quantity of interest, right? We have multiple values. These are the training data I was talking about. And then we want to know the value on where the red cross is. We don't have training data there, but we have a lot of neighbors, right? So in this case, for example, we are selecting 6 neighbors, 1, 2, 3, 4, 5, 6. And then we are, in this case, computing the prediction in this point as an average. It's not a weighted average, but it's an average of the neighbors. So this is basically what this technique it's about. In our case, we are predicting the deposition plume I showed before after an hour since the release, given the initial condition which are source location and wind velocity. And we have this enhanced KNN-based approach that I like to call it, because we deal with different issues where we're trying to make the predictions. Because we are going to rotate the plumes, we need to get rid of the buildings imprint. If you remember, I show a picture of the city and we have these buildings. And of course, where the buildings are located, the physics model does not predict the position. However, if we are trying to use KNN and we are trying to improve our predictions by translating our neighbors, we need to do that. We need to put some values there. And the way we did it, we impute those values using random forest. So we have a prediction there where the missing values are. And then the second step is to identify what case we are interested in. For example, we will have like a source location and a wind condition. And then, given the initial condition, we will find the neighbors, right? As we discussed before. And then the fourth step is to translate these neighbors to here, to where we are interested in the prediction. Then we rotate the plume in the direction of the wind that we are interested. And then we compute the outcome of the prediction as the weighted average of multiple plumes, and that's the prediction. And this is an animation of how the predictions look like. So here in the left, we have the true plume, and at the right, we have the prediction plume with, in this case, 4 neighbors. And you can see that the model does a good job with the prediction. This is a training data set of 2,000 cases. The computation is fast with the plotting and everything. We are less than 5 seconds, and we have a root mean square error of 0.5%. And the predictions are conservative. As you can see, the plume tend to be wider than the true plume, which is desirable. We want to be conservative in this case. And then I will go to the part of the talk that talks about how we assess the performance of our models in this for this kind of applications, atmospheric science applications. And this is new to me. I recently joined the team, and they have like their own data, their own way to assess the prediction of models. And one of those is the figure of merit in the space, which basically in this case will be the intersection divided by the union of the plume, right? The intersection between the truth and the predicted divided by the union, right? Well, normalized root mean square error, I'm pretty sure everyone is very familiar with what it is. Then fraction of data, this was new for me. What the fact too, what these two can be changed, but basically you are only considering good prediction, the prediction that are a distance where the ratio between the predicted and the truth is between 0.5 and 2. So you don't want the prediction to go further than that. Then we have fractional bias and well, coefficient of determination. This is a known one. And then some metrics as rank, which are average of metrics. In this case, for this particular problem, these metrics will depend on the number of data points we have. If we have more neighbors, we have more to choose from, and therefore, of course, the model will perform better. And then also depends on the number of neighbors that we use. More neighbors may be more accurate, but also more expensive. So let's go first with the figure of merit in the space, FMS. So this, as I said before, we have the predicted plume, the true plume, And we are interested in the intersection, which is this area in the middle, divided by the union, right? So the best, the ideal value for this metric is 100% or 1, right? And you can see here for, I don't know, we took 300 test cases, and we are roughly, the median is 75%, and the mean is 60 something. Usually for our applications, at least you want more than 60%, but it will depend on the problem. Then we have the normalized root mean square error. In this case, we normalized for the range normalized. So we took the normalization is done for the maximum minus the minimum value of the truth. And something I wanted to show here, of course, well, the ideal value is 0. We don't want to have an error, a departure between the truth and the predicted. But here you see how it varies as the number of neighbors increases, right? Like this is in percentage, and like with one neighbor we have a lot of dispersion, and we as we increase the number of neighbors, it's get less dispersed and more, and the error decrease, but then it doesn't change much after some time. So maybe you don't want to go to have like 21 neighbors. Maybe with 5 or 7 it's enough. The other metric is the fraction of data. And the fraction of data, it's, for example, here I highlight, this is the predicted plume and this is the true plume, and I highlight the data that will be good predictions, right? So we have a lot of points here, and these are the points that we will consider in the upper part, and then the rest will be, well, the rest of the points, right? So we want to maximize the number of points that lies in this part of the plot. Another metric is the fractional bias. Basically, we the ideal is 0. We don't want to have bias in our predictions, and this quantifies the departure from 0, right? And you can see here, this plot shows predicted plume over true plume, how the data aligns here. This part, we will have like a predicted plume that has like higher values than the true plume, and here the opposite, right? And we want to maintain ourselves in the 45-degree line. Another metric is coefficient of determination, the slope and the intercept. For example, here we have the same plot as I've been showing. However, we have and we can compute the intercept and the slope of these plots, right? Ideally, the intercept, we want a 0 intercept, and we want a slope of 1, a 45-degree line. And as you can see, as the number of neighbors increase, these metrics are tending to the ideal value, right? And you can see also the dispersion in the data. So, and rank is also something that is very common, which you do an average of multiple metrics, in this case, figure of merit in the space, fractional bias, and fact 2, and you get an assessment of that. And well, as a summary, I introduced the KNN approach, and I introduced some performance metrics that are usually used, and it's important to use, when you have a model, to use multiple of these prediction metrics, because each of those will give you a different information and you want your model be performing good throughout the option. So that's why it's important to do that. And at this point, I will take questions before I pass to the next topic. If someone has some questions, I will happy to answer.
Yeah, I have a question, Giselle. You know, how do you know, with this nearest neighbor technique, how do you enforce, neural networks? There are physics-informed neural networks where you can enforce mass conservation, for example, or momentum conservation. Is there a way with this KNN nearest neighbor technique to enforce mass conservation? For example, you know, you had a deposition in your plume. Is there a way that you can ensure that you're not depositing more or less depending on how you basically average your nearest neighbors?
That's a great question. Actually, we don't do that. We don't enforce mass conservation, but this is a great point. I think it would be possible to do, right? I don't know. I think we were like more concerned of like having decent predictions, but I think that's it's something that can be done, right? Because we do have the information in the training data. So like we, I guess we know in advance how the amount of mass that is released, right? So I guess yeah, that's something that we definitely can explore. We haven't done it, but yeah, thank you for the feedback. Actually,
yeah, I think it would be interesting
yeah,
to do that.
Yeah, thank you.
Thank you. Great talk.
Okay, so for the sake of time, let's continue. This is the second part of the topic.
Can I ask another question, please? Can I ask another question, please?
Oh, I'm sorry. Yes, of course.
Yeah, just a quick question. When you are, how can we measure the amount of data for training? Because sometimes is it randomly, or there is an analysis to be sure that this amount of data will train well the model? Yeah, thank you.
Yeah.
And even for the testing set, how measuring the amount of data for the testing?
Yeah, like I guess your question is how you determine how much data you need for a good prediction. Is that correct? Okay.
Yes, please.
Yes. So we initially didn't know. Initially, we had 2,000 simulations, and we kept getting data. At a certain point, we ended up with 12,000. However, we needed, this was the deliverable for this project was a software that needed to be online. And so there's a cost associated to have like ridiculous, like big training data. So at the end, we were only using 2,000 neighbors, right? So we didn't have, so initially we just keep computing simulations, and we didn't see that the error was decreasing substantially as the number of training data points was added. So we just took the amount of neighbor that was giving like a reasonable error and for our application, and that was around 2,000. But yeah, we didn't know a priori how many neighbors we needed for this application. This method, though, it's very robust because, as I was mentioning, you are moving the plume, right? So even if you have like 10 neighbors, your prediction won't be horrible, right? So because you even if the neighbor is far, let's say the release location is far and the wind direction is off, because we are rotating and translated, actually the neighbor become closer. And like you have another issues, for example, because the plume is not so close, you will have part of the plume that are outside the domain, right? So when you translate, you will have a truncated plume, right? You have that issues, but actually the model performed well with a few neighbors, but it was throughout the process that we were able to assess how many simulation we need to compute.
Yeah, thank you very much. Yeah, the model always it performs always good with small amount of data, but yeah, and so basically the answer is by trials. By trials, you can measure the prediction.
Exactly. At the beginning, you have an expectation. You say, well, this has potential, right? Like I will try, and we were lucky that we had a lot of data, and we realized actually we don't need that data because we did the uncertainty quantification and assessment, and we saw that actually most of them. I'm not showing it here, but we did it as the number of neighbors were increasing, and after 2000 you couldn't actually see the difference. So I would say that that was our assessment of how many data we need. But yeah, it was something that happened not before, right? We did already had the data.
Okay, yeah, thank you very much.
Thank you for your question. Okay, and what time is it? Okay, so these uncertainty bounds for multivariate machine learning predictions on high strain brittle fracture. Because we are late, I will just go very fast in the introductory. So I guess the important thing that you should have in mind is that we have this, the problem of interest is a flyer disk that will hit another disk. So there are two disks and they impact one into another at very high speed. It's 0.7 kilometers per second. And that will do a lot of damage to the target plate. And we are studying how the target plate will be damaged, right? And you can see here, I tried to include some videos, but I had problems, so I put 3 frames. So this is time 0, at time, and this is final time. And at final time, this material breaks here in the middle part of the flyer. And the flyers are disk. We are simulating in 2 dimensions, but are actually 3D disk. And well, these are like the aftermath of the experiments. And the goal in this case was to upscale a lower fidelity model using some simulations of a higher fidelity model. And the goal was to accelerate this high fidelity model. We couldn't afford to run this higher fidelity model. So we actually are improving the lower fidelity model by adding a better damage model using machine learning. And this was done based on Jewell 1994, right? Which what they do is correct the damage model using an effective elastic modeling. And for doing that, we need 2 quantities of interest. We need the length of the longest crack as a function of time. This is given by the higher fidelity model. The lower fidelity model doesn't give you this information. That's why we need it from the high fidelity model. And we are, we will use that in our machine learning model to inform the lower fidelity one. And we have the length of the longest crack as a function of time. As you can see, the material, the length doesn't increase until like everything happened very fast, right here in the middle. And then we have the tensile stress, which is another quantity that we will need to build the machine learning model. And this is the model. It's very simple. It's a multivariate, and this means that we have two quantities of interest, as I said, the longest crack as a function of time and the tensile stress as a function of time. This is a feed-forward neural network with two hidden layers of 200 neurons. A different emulation was trained for each. Okay, well, we did some testing with different embedding dimensions. I'm only showing equal 10, which is the number of time steps that you are considering. For example, you give 10 time steps and you will get 10, and with that 10 prediction, you will obtain the next 10 and so on. Well, we have a lot of parameters, and basically the way we did it was we have the length of the longest crack and the stress, right, for time 1, and we put it like in this format, and we train with like the first, we give the network 10 time step and we predict 10 and so on. And yeah, like this is the issue with this model, with the neural network model, is no uncertainty estimate in the prediction. So the model would give you a single value, right? And how we assess the uncertainty, how we can put bounds to this black box model. Right, and as we can see, it has like 45,000 parameters, right? So it's not easy to go and dig inside of the model. So what we used was the heteroscedastic loss function for the uncertainty. So we assume that each prediction can be modeled as a normal random variable. And this is the shape, which it might sound familiar to you. So in this part of the heteroscedastic loss function, we have a weighted MSE, right? So we have the difference divided by the variance, but we also have a part that penalizes that variance, right? So we have like two parts of it. And we have this multivariate case for this paper that I will show in the next page. I will give you the reference to the paper. We are using the multivariate heteroscedastic approach, and the novelty of the paper was to extend from a single output to predicted to multiple outputs, right? So this is the formula for a single output. You can rewrite this formula as for multiple outputs as a matrix in a matrix shape, and then for two outputs has this. You can rewrite it like this, right? And this is what we use in our case. And as I was saying, this is the paper, and you can, I'm a co-author of the paper, you can go and see the details there. But basically, we present the R square, right? The R square seems to be doing okay. So for the predictions of the longest crack, it's almost 0.97. Then we have a little more error in the stresses. However, this only considers the errors in the predicted value. So we want to assess the performance on the uncertainty, how well we are performing the uncertainty estimate. And that's what we did in this with this plot, right? So the ideal relationship is like in each ventile, we have a 45 degree line, right, of the coverage, right? However, with this approach, the approach that we implement, we are actually overestimating mainly our uncertainty, but that's not that bad, right? Because well, it's better to overestimate rather than underestimate it. But as you can see here, is the predictions do include the 45-degree, so it could be considered actually a success in the way that we are predicting the uncertainties. And in this particular, this box plots, well, it's for the case where you use 10 time steps over 20 repetitions. Each of those are for 20 repetition of the model. And well, the summary for this part is, so we use this heteroscedastic loss function for assessing the uncertainties in the multivariate neural network model, and we got conservative uncertainty predictions that yeah, like but it was a success because we were able to estimate uncertainties. So it was a way to tell the person, okay, I got tell as an outcome, okay, my neural network gave me the value of 5, but I can give you like an interval of confidence for the prediction. And that finalizes this part of the topic. So I will be happy to take questions now.